Hello and welcome to this press briefing on the James Webb Space Telescope. I am Karen Fox with NASA's Office of Communications, and we are here today at NASA's Goddard Space Flight Center in Greenbelt, Maryland, to talk about the latest update on the Webb telescope, which is all about aligning the mirrors. We will be taking Q&A from the media on the line after some talks today. You can get in the queue by dialing *1. We are also taking social media questions. Just post your question using the hashtag #UnfoldTheUniverse, and we'll be taking some of those along the way as well. We are going to start out with Thomas Zurbuchen, the Associate Administrator for Science at NASA headquarters in Washington, D.C. Welcome.
I'm so glad to be here. What a day, Karen.
It's exciting. Tell us why we're here.
Well, look, this is one of the most magnificent days in my whole career at NASA, frankly, and for many of us astronomers, one of the most important days that we've had. Because even though there's still weeks and months ahead to really fully unleash the power of this new observatory there at L2, today we can announce that the optics will perform to specifications or even better. It's an amazing achievement.
Fantastic. Tell us a little more about how we got here. What brought us to this day?
This has been a journey for over 2 decades. And you know, I go and look at this team. They're sitting there right now, and each and every one of them is so important, from different organizations, from Goddard, Space Telescope, Northrop Grumman, Ball, which spend work on this, and other contractors, other participants from all around. But for everyone who sits there, there's tens, hundreds that have contributed to this from the idea stage 20 plus years ago, with 10 plus new technologies that had to be invented, coming up with this fragmented mirror, 21 feet across, 18 pieces at the flatness not conceived before, and now putting it together to get to this place, of course, launching from Kourou together with our international partners, deploying it seamlessly in space, and now aligning that optics.
That's great. I've heard you talk a lot about this team and your admiration for this team. And my understanding is this is really the first time we've ever done this, where we've had to fold a mirror and put it up into the fairing before launch. And talk me through that a little bit. How much had to be conceived of and brought to where we are?
Look, I mean, when we have a mission normally elsewhere in our portfolio, we think of like 1 or 2, I call them miracles, you know, kind of new ideas, entirely new technologies that when we start, we don't know yet whether they're going to work. This telescope, this observatory now had 10 of them, perhaps even 12, depending on how you count. And you should know that the ingenuity of the entire team, you know, the diverse team that came together, the best that they offer from the international community, got us here. You know, for me, when I think about this, frankly, I've said it before, I'm saying it again, I think of that amazing challenge really at the edge of what's possible. And they did it in a way that, frankly, to outside observers, make it look easy. And what people should see is not that it's easy. That would be far from the truth. I've lost sleepless nights over this. This particular step, but also other step that this team put behind them in a fashion. What you should see is just the amazing quality of a team coming together, united behind a purpose, and you know, a desire to see the universe in ways we've never seen before.
So what's next?
Well, so this team is going forward. It's doing the entire optics alignment, continuing and finalizing it, and then of course it's all about instruments. Now we need to turn on these instruments in all the modes that are there, kind of somewhere in the summer, June, July perhaps, you know, we're going to have kind of these modes there. We're going to be ready to really show that universe that we've not seen, that infrared universe at that resolution. And then, frankly, what we're most excited about is turning it over to the science community to let the discoveries begin at a level we've never seen before.
Thank you so much. I really appreciate it. Thank you. We are going to keep Thomas here. He'll be here for the question and answer portion. But for now, we are moving on to the rest of the panel. We have a great panel here for you today. We have Feinberg, who is the Webb Optical Telescope Element Manager here at NASA Goddard. We have Erin, who is the Webb Program Manager at Ball Aerospace in Broomfield, Colorado. Marshall Perrin, the Deputy Telescope Scientist at the Space Telescope Science Institute in Baltimore, Maryland, and Jane Rigby, who is the Webb Operations Project Scientist, also here at NASA Goddard. We're going to start off with Lee, who's going to tell us a little bit more about this alignment.
Thank you, Karen. Well, we have now finished the 4th and 5th phases of the telescope alignment. We call those phases coarse phasing and fine phasing. And that's where we've made the primary mirror, all 18 mirror segments, into a single primary mirror. And we've initially aligned the telescope to the NIRCam instrument. That's the instrument that we use to do the alignment. And we've taken our first images. In fact, the team gathered over the weekend when the first images came down. We were in the Mission Control Center, and it was a very emotional moment. We kind of blew some of the image of stars up and really could see how it was performing. And I'm happy to say that the optical performance of the telescope is absolutely phenomenal. It is really working extremely well. And we said last fall that we would know that the telescope is working properly when we have an image of a star that looks like a star. And now we have that, and you're seeing that image. This is actually a 2100 second exposure taken at roughly 2 microns, which is the wavelength which Webb was designed to work at or above. And you not only see the star and the spikes from the diffraction of the star, but you see other stars in the field that are tightly focused, just like we expect, and all sorts of other interesting structure in the background. We've actually done very detailed analysis of the images we're getting, and so far what we're finding is that the performance is as good, if not better, than our most optimistic predictions. So we're really pleased with that. And to give you some perspective of what has happened and sort of how the telescope got here, we want to run this video clip to kind of show you what the telescope has been through to get to this point. Webb's science objectives required a large primary mirror, a mirror too large to fit inside the largest rocket fairing that exists. So we had to design Webb's optics to be folded. This meant Webb's mirror segments had to be extremely lightweight and individually controllable so they could be aligned in space. We put everything through rigorous testing to ensure Webb's delicate systems would survive launch and work in the supercold vacuum of space. Webb's cryogenic test inside Chamber A at the Johnson Space Center in Houston in 2017, 5 years ago, was actually the last time we tested the telescope or took images with the NIRCam instrument, which is used to align the mirrors. At Northrop Grumman in Los Angeles, Webb's optical segment was integrated with the spacecraft and sunshield segment, and we did more testing. One thing we can't directly test on Earth is the effect of zero-G on the system. We used computer models. These models gave us confidence it would work in the zero-gravity environment of space. We packed Webb and shipped it out from Los Angeles to the Panama Canal to the Guiana Space Center in French Guiana. There, Webb was placed atop the Ariane 5 rocket and launched into space on December 25th.
And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds.
This is the first time the Webb Observatory was exposed to the vacuum of space, the heat of the sun, and zero gravity. Moments after launch, the solar panel deployed. For the next several weeks, the Space Telescope Science Institute team unfolded about 50 parts, including the sunshield and the mirrors. The open sunshield helped cool down the instruments and mirror to about minus 400 degrees Fahrenheit. One of Webb's final deployments was releasing the mirror segments from their launch locks. Then we could start the mirror alignment process. For the next 6 weeks, the optics team worked to perfectly align Webb's mirrors. We had to engineer the telescope and mirrors to survive all of this and meet demanding optical requirements. So this achievement was not an accident. It took a lot of hard work and just a total commitment to excellence by a number of teams. For over 20 years, I've been fortunate enough to work with teams from Northrop Grumman, Ball Aerospace, L3 Harris. 4 different NASA centers contributed to this, as well as SAO, Space Telescope, and many other companies, as well as our collaborations with the European Space Agency and the Canadian Space Agency, and all the interfaces and all the aspects of the telescope. And with all that hard work and dedication, We can now say it was worth it, that the telescope itself is working. We still have work to go to bring on the rest of the observatory, the rest of the instruments, finish the alignment of the telescope to the other instruments, but the optical performance is working, and we're getting very close to the point that we can turn this amazing scientific tool over to the astronomical community. And we kind of want to leave with the thought that not only have we built this amazing scientific capability for this generation, but we've sort of pioneered a new way to build large space telescopes, which we can give to the next generation and future generations. Thanks.
Thank you so much, Lee. We are now moving on to Erin Wolf, who is the Webb Program Manager at Ball Aerospace. She's going to give us some details about the engineering that made all of this alignment happen.
We're seeing the payoff of years of technology development. The optical hardware that we spent years manufacturing and polishing and measuring down to the tens of nanometers is working better than our most optimistic predicts. It's very exciting. We also spent a lot of time developing the algorithms and the mathematical processes that we would need to perform this alignment in space. You know, we've never had a segmented telescope in space before, so we had to invent a whole new process. So we built a 1/6 scale model of a testbed telescope in Colorado to prove out all of those algorithms and run through the process that dictates what our mirror moves will be on the motors. And it's actually been easier in space than it was in the lab. So we use the motors on the back of the mirrors to make small adjustments to the mirror positions. And we also have that center radius of curvature actuator that can actually change the curvature and shape of each individual segment as we align and tip and tilt and piston through focus and move them all around. And the goal here is to get all 18 segments to work together as one big monolithic primary mirror. And you can really see the progression of this process through our pupil images. So a couple weeks ago, we took this pupil image. And you can see one segment's really lit up brightly with some starlight coming in, but now we have a new pupil image with all 18 segments just lit up, and it looks wonderful. So we're really excited. So far the process is working, and the hardware is performing better than requirements. We couldn't be happier, and it's just a testament, like Thomas and Lee have said, to all of the years and years of hard work that everyone has put in. People that aren't necessarily on the team now for the commissioning, but they did the technology development decades ago, the integration for many, many years. So it's really an honor to bring Webb through this process now at the end and work on all of that amazing technology development that the team did back then.
Thank you to Erin. We are now going to move to Marshall Perrin with the Space Telescope Science Institute. He's going to give us more details about the alignment.
Thanks. So the alignment process began after the initial deployments of Webb back in the first few weeks of this year. And those large unfolding motions that got the mirrors out to about within a millimeter or so of their desired locations. But in order to have the mirrors all act as one, they need to be lined up to just within a few nanometers of one another. That ends up being, it's a few hundred atomic diameters, the level of precision that we need here. So to do that, we step through a long process that the team has been preparing and practicing for many, many years, in which we begin by finding the 18 spots of light, one from each of the mirrors, and we gather those together. We begin by aligning them all as if they were separate telescopes. We have 18 telescopes basically at this point. We're going to focus and align each of those telescopes one by one, using defocused images to work out the misalignments of the mirrors and bring them to the point that each of these 18 telescopes are sharp on their own. Once we do that, we begin to stack together the spots of light. And this we call image stacking produces something that has the light gathering power of the full telescope, but not yet the sharpness. We still have the mirrors misaligned by some hundreds of microns at this point in the process. And we need to refine that alignment through a series of additional measurement steps and measure, correct, measure, correct. We use several different measurement techniques. We move the pattern of spots around the different parts of the telescope in order to measure the secondary mirror alignment between the center and the corners of the field of view. We use a prism to split the light from pairs of segments and measure the piston offsets. We can then correct those piston offsets to bring the mirrors into phase with one another. And at the end of the process, we use a set of defocused images that we take using lenses we put in the beam. And this is sort of like being at the eye doctor, and you test different lenses and see how they work. And here we're using computer and mathematical analysis to use those defocused images to measure the mirror positions with the precision of just nanometers. And we use that to dial in these very fine adjustments that bring the telescope into just an exquisite sharpness. This is a process that we've prepared and practiced for years, and we've rehearsed over the last few years, and now we've had a chance to run that plan, and it's just an absolute thrill to be able to say that everything worked. And the telescope, at no point in that process did we have any significant technical issues with the telescope. Everything's performing at or above the expectations, as was said. There were a couple places with some surprises in the data, but little surprises. The biggest one, honestly, has been just how closely it matched the models and the predictions from the ground. It has been far closer to those predictions than a lot of us had dared to hope. And we now have achieved what's called diffraction-limited alignment of the telescope. The images are focused together as finely as the laws of physics allow. This is as sharp an image as you can get from a telescope of this size. And as we were focusing the telescope, we were using typically one bright star at a time, a handful of different stars we used on the sky. But as we were focusing on those bright stars, we couldn't help but see the rest of the universe coming into focus behind them, to see the more distant stars and galaxies coming into view. And honestly, the team was giddy at times just seeing this happen. There's no way to look at these data and not be excited at the scientific possibilities that are opening up here. We've done this over the last several months within almost exactly on schedule. There's a few things that took a little bit longer than we thought. There are some steps that went faster than we thought. And so overall, we're really within just a few days of exactly where we thought we'd be at this point, about 3 months after launch. And that sets us up to be on track for completing the rest of commissioning within the 6 months after launch and turning over to science starting midsummer. It's an amazing place to be.
Thank you so much, Marshall. We have one more speaker to talk a little bit about that science that Marshall was discussing, but just a reminder, after that, we will be taking questions. For media on the line, you can press *1 to get into the queue. And for social media, post your questions with the hashtag #UnfoldTheUniverse. Thank you so much. Next, we have Jane Rigby from NASA Goddard.
Thank you, Karen. So you've heard from the other speakers, but I'm just going to say it again. The telescope performance so far is everything that we dared hope. The optics work. The goal here was to build a telescope 100 times more powerful than anything we've had before. From the early engineering data that we have seen so far, we know that we're on track to meet those very demanding science requirements. The engineering images that we saw today are as sharp and as crisp as the images that Hubble can take, but are at a wavelength of light that is totally invisible to Hubble. So this is making the invisible universe snapping into very, very sharp focus. The requirement was to get to the diffraction limit at 2 microns. We nailed it. For the astronomers who are listening, at 2 microns, the point spread function has a full width at half max of 2.3 pixels. That's 70 milliarcseconds. The only way to make those images sharper is to just make a bigger mirror. Now, we took this image to characterize the sharpness, but you can't help but see those thousands of galaxies behind it, right? They're really gorgeous. Webb can't, there's no way that Webb can look for 2,000 seconds at any point in the sky and not go incredibly deeply. So, this is going to be the future from now on. Wherever we look, it's a deep field. Webb is seeing back in time to galaxies that were seeing that light as it looked billions of years ago without even really breaking a sweat. So where we are right now, we have not taken any science data yet. We are still commissioning. And so what does that mean and what's next? So right now the telescope is aligned to NIRCam, one of the science instruments. We now have to align the telescope to all 4 of the science instruments. So every one of those 4 instruments is getting a crisp image. And these 4 science instruments we have to get ready for prime time. We're getting them ready for science. One of those 4 science instruments, MIRI, which eventually is going to be the coldest thing on the observatory at 7 degrees above absolute zero, it's still cooling. So we're cooling that instrument, and we are taking the science instruments through their checkout period. And so, this is the process where we know that yes, these instruments are working to do the science that we need them to do. So the transition to science will happen in July, where we finish commissioning and we move into a very demanding year of science operations. We have already selected, it's prepared and ready to go, a year of really compelling, demanding science with this telescope. And I'm just so excited to see this science, which was competitively selected, right? We received more than 1,000 proposals. We picked the very best ones. So that science is going to be studying galaxies that where we're seeing the light, as we're seeing these galaxies, they're so far away that we see them as they looked only a couple 100 million years after the Big Bang. So we're seeing back in time. This is what we're going to be doing in cycle 1, to understand how galaxies like our own Milky Way formed and then evolved over 13.7 billion years of cosmic time. Webb will be studying planets that orbit other stars. And more than that, we'll be able to study the atmospheres of those planets to understand what they're made of. You know, a lot of our science is going to be understanding what stuff is made of through a process called spectroscopy. You know, what are the atmospheres made of? What are galaxies made of? Fundamentally, this telescope is going to explore how we got here and what's out there. And you know, what's out there in our gorgeous universe, and that's just starting to come into view now.
Thank you so much, Jane. We're going to move on to the question and answer portion. We're going to open up the mics for the first question, please. If we don't have our first question, I can pull up a social media question, but let me know. I'm going to go to a social media question while we work that out. We have a question from Peter on Facebook, who is asking, what about pointing the telescope at different stars? How is it going to rotate? Are there actuators to facilitate this, or does the entire spacecraft move?
You want to take it, or should I?
Yeah.
So the way Webb moves, some people think the telescope moves with respect to the sun shield, but that's not the case. The telescope and the sun shield all move as a single object, so the whole observatory tips and tilts to move across the sky. The way that happens is there's a thing called reaction wheels. These are, in essence, big spinning wheels like a gyroscope within the body of the observatory, and they spin one way to spin the whole telescope the other way. And that lets the telescope track across the sky. We then have a fine guidance sensor. That was the contribution from the Canadian Space Agency that locks on stars and stabilizes the images, moving a mirror that adjusts within the third mirror within, the fourth mirror within the telescope, tips and tilts in response to the signals from the fine guidance sensor to lock onto the different stars. And that's also something we've tested out over the last few weeks, and it's working very well at this point.
Great. Thank you so much. We seem to have worked out the problem with the phone lines, but they should be on now, so we'll take the first question.
And our first question comes from Seth Bornstein from the Associated Press. Your line is now open.
Yes, thank you for doing this. I guess this is for Jane. That first image, can you first tell us what star is this? How far away is it? Has this star been seen with Hubble or any other telescope? And what is the difference between the image you're showing and whatever knowledge we've had in the past? Mm-hmm. How much better or such is this? And how much in the past is this star? And how many galaxies are we seeing in the background?
Sure. So we sort of plucked this star out of obscurity. It was minding its own business. It is up looking out of the plane of our solar system. And we picked it because it was convenient for the wavefront folks. It is a nice, boring star of about the right brightness.
It's the right brightness, and it's off by itself with no other bright stars nearby. It's a pretty much generic anonymous star in the sky that worked well for the kind of sensing measurements we needed to do. The brightness of that star, it's about 100 times fainter than than the human eye could see. And that's the one that looks so blindingly bright in this image to get a sense of how sensitive the telescope is. I don't know, I can get back to you on how far away that star is, but we think it's sort of just a generic average star in our galaxy.
And then what was known behind that, because this isn't a famous deep field. This is just, we've made it a fairly deep field, but it was just a star. So the brightest stars in that image are known in previous surveys, the brightest galaxies. Everything else there is new.
I'll just add with, again, this star is one of many stars we used throughout the commissioning process of Webb. We've gotten a lot of questions about the stars we're using. They're generally picked out not because they're special stars, but because they're the right brightness and in the right parts of sky for our engineering tests. They're not, intentionally at this point not special stars. They're just, here's a generic star we can use to focus the telescope.
Thank you very much. We will go on to our next question, please.
Our next question is from Chris Jebhart from NASA Space Flight. Your line is now open.
Yes, thank you so much. Wondering, looking out a little bit ahead to the rest of the mirror alignments, you mentioned that you have to align it to each of the instruments. So I'm wondering, is each time the telescope observes something, do you have to basically realign it to each of the instruments, or are you trying to find one alignment that works for them all? And in particular, like how would that work going forward with practical observations in terms of seeing all the way back and seeing very, very close objects in our own solar system?
Seems like an Erin question.
Yeah, I can answer that. That's a good question. You know, we initially aligned to NIRCam as an instrument because it has some of those special optics in the filter wheel that Marshall mentioned, just for our alignment process. Now that we've gone through that fine alignment process with NIRCam, we will take a look at the other instruments across the field of view, and we'll balance the alignment of the entire telescope to all 4 of the instruments so that they're all in focus and they're all nice and sharp. But once we're done with that process, then we leave it alone, basically, and we only do maintenance operations, is what we call them. So every couple days, we'll take a measurement and see how the alignment looks, see how the wavefront looks, and if it's drifted a little bit, maybe for thermal drift or other reasons, then we can make a tiny correction. We'll still be making only nanometer size moves at that point, so we won't be realigning the telescope. We'll just keep it in focus and maintain it throughout mission life.
Thanks. We are ready for our next question.
Thank you. Our next question comes from Alicia Salter from Mashable. Your line is now open.
Hi, thank you for doing this and congrats. I was hoping just for the general public, could you explain the features of the image? In other words, what's causing those big, bright spike structures and what's giving the image its red color? Thanks.
Yeah, so I can help you a little bit. So first of all, the color, that's actually the colors that we used, the engineers used to display it. But the actual light that's coming in is infrared light, which you would not normally be able to see with your eye. So we wound up using red to help us see the contrast in the image, and that's what we're displaying here. But in terms of what the spikes that you see coming out of the star, any telescope that has special structures like the shape of our mirrors will have that kind of spikes in it. Those are actually the result of, in this case, having hexagonal segments. So we have these 6-sided mirrors, and we also have our struts, the things that hold the secondary mirror up. And because of the sort of the waves that light travels in, that actually causes something called diffraction that makes those spikes. And you see that most intensely when you have a very bright star. In the other stars in the field, you don't see it as much because they're dimmer and those effects are harder to see. And that's why you only see it in that very bright star.
Thank you so much, Marshall. We are going to continue with some more media questions. Next one's up.
All right, and our next question is from Bill Harwood from CBS News. Your line is now open.
Hey, thank you very much. Yeah, I just want to follow up on an earlier question because I'm still a little bit confused about the alignment to date and then what has to be done for the other instruments. So I'm taking it that you're perfectly aligned for NIRCam, and the focus is as sharp as Eleanor said, as sharp as you can get it. But are you moving? I don't understand if it's the secondary that you will move at this point or individual segments to achieve that focus for everybody. I guess I'm just not visualizing how that works or how the internal mirrors in Webb play into all of that. Thanks.
So the primary things we're doing that are still in front of us, the secondary mirror right now is actually fairly well aligned. And we know that not just because of the star that we just showed you, but the other stars in that field tell us it's pretty well aligned. But we want to make it, you know, as good as possible so that it's balanced for all 4 instruments. So we do have to do a little bit of very small tweaks to the secondary mirror alignment. And then also the instruments themselves, several of the instruments have the ability to focus internally to the instrument. And that's something we still need to do, is to get them focused once the telescope itself is fully aligned and fully focused in a way that balances all 4 instruments. It's a very minor change that's in front of us, but when you're trying to do sort of transformative science, you have to really get to the ultimate performance. And it'll be a few weeks to do this, but we will be able to leave the telescope from that time forward.
Thank you so much, Lee. And we will move on to our next question, please, from the media.
Our next question comes from Eileen Woodward from WSJ. Your line is now open.
Hi, thank you so much for this. I just wanted to ask, do you think that you have sort of passed the performance Rubicon in terms of between now and June and July, when you expect to start scientific observations and see first imagery of that deep universe? Do you anticipate any problems between then and now? Like, it seems to me like coarse and fine phasing were sort of the big thing that we wanted to achieve, and you've done so. But I'm curious if you anticipate any issues between now and then.
We'll start out with Thomas for that question.
So I'm really interested in other answers, actually. I just want to tell you, of all the sleepless nights I've had and kind of the worries I've had, they're all behind us now. And it's not because there's no path ahead. There's still mountain to climb. There's important tests that need to be done and important things that need to be proven, such as the alignment. As also all the modalities in each one of the instruments needs to be tested and calibrated. So there's important stuff ahead. But I want to tell you, you know, kind of what's behind us. We're way up that mountain now. We're way up that mountain. Yes, there's a path ahead. And, you know, in our world, there's always a path ahead. We never go say, we're done, we can take it easy now. So kind of the way we create success is by, frankly, focusing on the issues that are still ahead and we're worrying about. But I'm interested in other opinions or other statements to that.
Well, I do want to say one thing is, you know, we do know now that we built the right telescope in terms of the optics. That is not going to change. And that's something that the fine phasing process has brought out. We've been able to analyze those images, and we know we built the right telescope. And of course, you know, that's a big deal. And so that's partially why we're here today. But as Thomas said and others have said, you know, there is work to go. So we're not there on the entire observatory. But just to take that image, you know, that was a 2100 second image. A lot of things had to work. We had to be able to point. We had to be able to, you know, guide, which means kind of track on that star precisely. It was a fairly long period of time that we took that image. So there's a lot of things that are working really well, but there is more work to go.
All right, thank you. We will go to the next question from the phone lines.
And our next question comes from Alexandria Witz from Nature Magazine. Your line is now open.
Great, thank you. My question is for Jane Rigby. Can you just fast forward a little bit more to sort of first science again? We hear dates of June, July. Can you be a little bit more precise on when we'll have more timing on which of those dates, which of those months is accurate? And also, what do we know about kind of the super secret first science observations that are going to be made? Have those targets been chosen? I know you can't tell us what they are, but have those targets been chosen?
Okay, in reverse order. Yes, the targets have been chosen for the super secret first images that will be released. The science targets, of course, have all been chosen. We've selected more than a full year of science, and those targets have been chosen, and those programs have been fully specified. The computer files that tell Webb how to take the data, we have all those in hand. As far as the specifics, we will start science operations when we are done with commissioning. Commissioning is nominally 6 months long. We launched on Christmas Day, so that would be the end of June.
Great, thank you. Moving on to the next question, please.
All right, and our next question comes from Passant Ravi from Inverse. Your line is now open.
Thank you. Yes, I'm wondering, with Hubble, we've seen all of these stunning images, but with James Webb, since it's looking at more distant objects, is the aesthetic value or sort of visual value less important and it's more about the data with these images?
Both and. They're gorgeous.
They're gorgeous. You can't help but enjoy seeing the distant universe. Part of why we're all astronomers is to study the stars, because many of us up here on stage, looked at the sky as kids or looked at pictures from Hubble and other telescopes and said, that's amazing. But in addition, we want to make the technical scientific measurements. And some of the measurements we make with Webb will be not as visually stunning. There will be series of lines. There will be the spectra. Some of the measurements with Webb will be, I think, even more stunning. Multicolor imagery. There's 2 instruments on Webb that have what's called an integral field spectrograph that gives you an image, but not in 3 colors, but in thousands of colors at once. And those are going to be some really neat data to see. And that's part of the complexity with calibrating the instruments. So I think, just like with Hubble, there are some Hubble images that we take that do have deep aesthetic value and that they have scientific value. And it's always a both and.
Yeah, and some of what we're getting from the spectroscopy, we'll be telling you how galaxies are rotating and how the gas in those galaxies is getting blown out of them by supernova. And we'll be determining what the composition of what the gas in galaxies is and the composition of the atmospheres of planets. So that, maybe it's a little bit geekier, but what you get out of it is really, really cool. So we will both be doing stuff that makes us giddy and happy and always gorgeous, and stuff where we say, oh my God, now we know what that's made of that we never did before.
It's a great answer. I'm looking for a lot of giddy and happy as we go forward. All right, we'll take the next question, please.
Our next question comes from George Dvorsky from Gizmodo. Your line is now open.
Hey guys, thank you very much for doing this. I just want to go back again to any potential issues that may still be encountered as the commissioning phase continues. And I'm just hoping that you guys could be a bit more specific. In particular, when it comes to the instrumentation, the upcoming steps, are there any potential points of failure that could really disrupt the unveiling of the telescope? And I know that Thomas already said that nothing's going to keep him up at night anymore, but I'm wondering if the rest of the team agrees with that. Are there any steps that are really still kind of harrowing or problematic that could really disrupt the process? Thanks, guys.
I could take that one. So, we've had days on this project where if it didn't work, we were going to go home, right? If the sunshield hadn't come out, well, then we don't have a mission. If the secondary mirror hadn't deployed, we call it secondary not because it's not important, but because it's the second after the primary, right? If the secondary hadn't come out, all that beautiful light coming into the primary was just going to bounce off into space forever. And we wouldn't detect it. So there were parts on this mission where it's like, well, this is going to work or we're done. We're past those points now. That's what Thomas was getting at. And we're now to the stage where if things don't work, we're looking at we're looking at partial degradation of the total science return. We have 4 science instruments. All 4 of them have turned on and said, hi, our aliveness check says we're okay. For 3 of those instruments, we have data. They're coming back. Yes, this is looking okay. It's early days. MIRI has to cool from, the temperature's in the 90s right now, 90 Kelvin, 90-something Kelvin. It needs to get down to 7 Kelvin. So that's something that I'm looking at, right? This has this closed circuit refrigerator that recirculates helium to chill MIRI much colder than the rest of the science instruments. So that's something where, okay, that's a big deal. We want to get MIRI cold. But we're now looking at where, yes, space is a dangerous environment, and Webb is up there in space, and every day we have to keep it safe, and there's work to do that. But most of what we're looking at going forward is if things don't work, we're looking at gradual degradation of the total return rather than shows over folks.
And a key thing about the telescope is the telescope feeds all 4 instruments. So when the telescope doesn't work, then that really affects the entire mission. And we're now beyond that point. Now, there's always the potential that some subsystem might, not work at some point. That happens, but we have a lot of redundancy in all of our electrical systems. So from the point of view of having a working observatory, as Jane said, we're in very good shape. And so now we're really going to be focusing more on individual instruments and bringing them online.
Thank you so much. We will take the next question from the phone lines, please.
Our next question comes from Marina Corin from Atlantic. Your line is now open.
Hi, everyone. Can you tell us more about the group that chose the top secret targets for the first big image release? How big is the group? Who is involved and from which institutions? And when exactly was the list of targets finalized? Thank you.
What I am hearing in the room is that we will get back to you on that, Marina. I don't know that we have the exact size and people at our fingertips, but I will follow up with you when this is over. You can drop me an email and I will get you what I can on that. Do you have another second question, given that we couldn't answer your first?
I do. Thank you.
Go for it.
Can you tell us, so we've heard a bit about the star at the center of this image. Can you tell us more about the galaxies that are in the background, you know, how far they are, and how does this compare to how Webb will see galaxies in the future? You know, how closer will it get?
All right, well, I guess I'm the galaxy geek in this crowd. Okay, so as we said, this wasn't a famous deep field. This isn't a place where we studied where we've known what's out there. Just eyeballing it, I mean, we got those data, they came down Saturday night, so I was eyeballing them Sunday morning in my pajamas. And yeah, they're like, you know, they're several billion light years away, but would actually have to take some spectroscopy to get you a better answer than that. We can do spectroscopy once we get the science instruments ready to go. And so that's the sort of thing that Webb will be able to do once we get into normal science operations. The NIRSPEC instrument, which was made by the European Space Agency, has this really cool microshutter array where it has 250,000 little doors that can open and close. And so it can take spectra of dozens of targets within that field. And so one of the key science capabilities that this telescope has is to target a field like that and pick the most interesting 30, 40 galaxies and say, I want a spectrum of that. And with that, you know exactly how far away each of those galaxies are, and depending how you do it, you understand how much heavy elements, carbon, oxygen, nitrogen, those galaxies have relative to hydrogen. So that tells you how many times the gas in those galaxies has gone through stars and then exploded in supernovae.
I'd like to add just one thing to that, which is that we picked this field just for the wavefront sensing calibration. It was not chosen for these galaxies, but all the data we're taking in commissioning is going to be public when we get to the end of commissioning in June. And so, you know, scientists out there, they're grad students at some university, can download these data in June and start answering these questions from this and all the other data that's taken during this commissioning process.
June or July?
June or July, okay.
When we get done.
When we get done. When we get past that, all of the calibration data, including these images around the fine phasing target in multiple wavelengths, we're just going to let that data out to the scientific community along with those other observations.
All right, we are going to take a few of our social media questions now. We'll take two. The first one is Torrin T on Instagram asks, what is the precision between the mirror segments now that they are aligned when it comes to the alignment?
Well, do you want to talk to that? That was in your presentation.
Yeah.
So our actuators have a resolution. We can move and maintain a motor position to about 9 to 10 nanometers. So that's our capability. And our sensing requirements and our sensing budget means that we aren't actually within 10 nanometers segment to segment. But I think we're down to 40.
We're below 100 nanometers easily.
Yeah, we're absolutely.
And that's over the whole telescope and the instruments.
Full system, yeah.
Over the full system. Yeah. So each individual segment to the other segment is well under 100 nanometers.
Yeah.
Great. Our second social media question is from Briannian Motion on Twitter, who asks, what, if any, are the lessons learned from Webb so far that we can take into the next space telescope? Are there any things that could be done differently?
Yeah, one thing about Webb, I mean, obviously it's a super cold telescope, and that really drove a lot of the design. Of course, that huge sun shield was needed to cool things down, but it's also a passively thermal telescope. And what that means is that unlike, for example, the Keck telescope, which is a ground telescope in Hawaii where they actively move mirrors, The Webb mirrors are designed to always just kind of be where they are, and then only every few days do we update them. And that made a lot of sense for a really cold telescope, but it also made it difficult to prove the telescope was going to work and to design everything from the mirrors to the structure that holds it. And so one of the things that we think in the future for these large segmented telescopes is we will make use of the types of things the ground telescopes have, which are active controls. And that would make our ability to test it easier, and it would make us also be able to make an even finer telescope, which some of the future observatories may want to do. For example, if you want to study exoplanets, particularly Earth-like planets around stars, which is one of the future missions that has been recommended by a National Academy committee, you're going to need a very precise mirror surface that's extremely stable. And so we were going to probably want to migrate from this sort of approach we took for this very cold telescope to a more active telescope.
All right, we are going to move back to the media questions on the phone line. We'll take the next question, please.
And as a reminder, to ask a question over the phone, please press star 1. Our next question comes from Ken Kramer from Space Up Close. Your line is now open.
Hi, thank you, and congratulations on the great results so far. One thing I was very interested to know was about the cooling, how far you come. It sounds like you're at 90K now. How long is it going to take you to get to 7K, which is your goal? And when can you? How long will talk about the commissioning of the science systems when you get to that point? Thank you.
I'm going to repeat that back, Ken, because it was a little hard to hear you in here. I think the question was how long to get from where we are now to the 7 degrees Kelvin, and also to talk a little bit more about science commissioning of the science instruments, correct?
Yeah, I mean.
Yes, that's it. Thank you.
Great, thank you.
Yeah. So the cooling process takes a couple weeks, and we actually will be using, once we have that mid-infrared instrument fully operational, we actually will use it to make sure that the telescope's balanced, sort of the last step, which our target was to finish in the end of April. But it takes a couple weeks to do the cool down, roughly 10 to 14 days, and then as we stabilize it, we'll start taking images and make sure everything is working right. There's a few different transitions that it goes under as it cools down. So it's a couple week process.
I'll just add the detail that the cooler has its own complicated calibration process. Just like the telescope has a multi-step process. This is not just a refrigerator that you turn on, but has its own, I think it's a 6-step process. And I believe they're right now on the 3rd stage of that cool down process. The 4th stage will begin about a week from now. And that's really going to accelerate the cooling of MIRI.
And did we really address what's happening with science commissioning next with commissioning instruments? Do you want to mention just what our next steps are? Yeah, it was just what's happening next for commissioning of the science instruments.
We covered some of that. Let's see. So science instruments, MIRI has to get cold. That is the really big one. We're walking through for each instrument, there's a set of activities that each one has to show that it is working. And it's things like stepping through the filter wheel and making sure that you get every position in the filter wheel that you want. Getting the darks, because to understand the properties of the detector so that we can take that out, so that we're seeing the sky and not what the detectors are doing. So there's so we're doing every step in that to get those instruments ready for science.
Thank you. We are taking 2 more media questions. We'll take the next one, please.
And our next question comes from Erin Klotz from Aviation Week. Your line is now open.
Thanks very much. I have 2 questions. Well, one question for Jane and then for Thomas. Are you seeing any impacts in the JWST science community over the situation in Ukraine? Are there any Russian astronomers, astrophysicists involved in any of that first-year science? And for Thomas, can you address that same question more generally to the NASA science program? Thanks.
So thank you, Irene. Unfortunately, I'm going to have to circle up with you afterwards. We're going to try and stick to some of the science and the alignment right now, but I will get you any information and updated statements we have. So I'll circle up with you as soon as we're done here. If you have another question, I would take it. Otherwise, we can go to the next one.
Oh, can Thomas not address that question either?
Yeah, we'll stick to responding offline.
Thank you. And our next question comes from Daniel Riguera from R Drone UI. Your line is now open.
Hi, how you doing? Thank you for this. Congratulations to all. I think this question could be for Thomas. And given the little lifetime of this beautiful telescope, NASA could be doing some plans to refuel the telescope to get more lifetime on this?
So you're right that every time we build a telescope, we think about how long we can operate it. I want to tell you that the delivery by Arianespace and the European Space Agency was just fabulous. Frankly, the lifetime of the telescope that we initially said at about a decade or so is, we believe, exceeded based on what we see there. As we're kind of learning how to operate and point in the sky, the estimates of the lifetime will really become more accurate. So as we come to the end of commissioning, I'm sure we'll give a much more accurate update. I don't know, Lee, whether there's anything you can say already now that you haven't already said. You were the person who talked about lifetime before, but that's what's on our mind.
Yeah, I think Mike mentioned during one of the press events that he thought it would be 20 years. And the one thing I can add is that on the actuators, they will last as long as the rest of the observatory. They're working exactly the way we expected. They have a very long lifetime, so there's no changes to anything in the sense of the lifetime of the system. Yeah, and I don't think there's any new updates, but as Thomas mentioned, as we go through commissioning, there might be some other additional updates from the systems team.
Okay, if there is opportunity to make a new question.
I think we do have time, yes. Go right ahead.
Okay, what will be the next target of when science starts on inside the solar system?
Inside the solar system. There is an early release science program to study either Jupiter or Saturn, to study the gas giants in our own solar system, and in particular their moons. So there is a program to do that has been competitively selected and is in the queue. We are doing some commissioning activities to go double check that we can look at a target as bright as a planet in our own solar system and still be able to point at and get data on the nearby orbiting moons. There are also some approved programs to do Trojan asteroids, and there's an approved program to study those asteroids that are interstellar visitors from our solar system, from other, asteroids that have come in from outside our solar system.
Right, Jane, and of course the reason these are such a high priority and they did so well in the reviews is of course, as we have other missions actually exploring the solar system, the information that we can get from this amazing telescope will really help us run these missions better. Lucy is on its way to the very bodies that you just talked about, and yesterday I met with the Clipper team that, of course, is going to launch in 2024, that amazing mission to go to Europa, which is one of those moons that you just talked about.
Thank you so much to everybody who has watched today, who was on the line asking questions, and who has talked to us today. We are going to finish up now. You can follow along and learn more about this amazing telescope and what's coming up this summer and all of the incredible science that we have talked about here today on nasa.gov/webb, that's W-E-B-B. You can also follow along in the social media conversation using #UnfoldTheUniverse. And of course, nasa.gov is going to tell you all about the way that Webb interacts with all these other incredible science missions and all that we're doing in the solar system and beyond. Thank you so much for being here today. Goodbye.